So let's start the first afternoon session of this workshop. This morning we had a very beautiful, complete and exhaustive talk on the future collider landscape by Stephen Gibson. And in fact, collider machines have been playing a central role in particle physics starting from the 60s, when the INFN Frascati labs play a crucial role. And Leah, we talk about it in the last talk of today's session, up to the celebrated last discovery at the LHC of the Higgs particle, the missing piece of the puzzle. Actually, the discovered Higgs is not the last piece of the puzzle, and many questions, as you know, remain open. In these last years, a new branch of research is developing and giving important results. The very first instance of our universe can in fact bring important information about the nature of our world. In a sense, the early universe is a sort of cosmological collider. Data collected by the interferometers are so becoming crucial for our understanding, and they are complementary to the collider data. The synergy between astroparticle physics and collider physics is a font of richness, and it will make possible a great progress in the near future. And this will be the topic of the next talk. It's a pleasure to have Julia Harz as a speaker. She's now working in the Munich University. Actually, she's in Aspen now. And we really thank, because it's early in the morning, right?
Yeah, 7:30.
And she will talk about confronting astroparticle physics and collider physics. If you have an urgent question, you can raise your hand and I'll let you I'll pass the question, but Julia told me that she will make a stop between two parts of the talk. So maybe the best thing is to have questions in this stop. Okay, please, Julia, go ahead. Thank you.
Yeah, thank you very much for the nice introduction, and yeah, apologies that I missed the first part. It's simply due to the shift in the time zones. Otherwise, I of course would have gladly joined also the morning session. And yeah, I want to talk about how we confront, or we try to confront, astroparticle physics with colliders. Of course, the title is huge. So unfortunately, I might not be able to talk about everything. Otherwise, I think it will be far too long and never be able to do it. So of course, my disclaimer is it's a personal biased selection, of course, of the recent developments in the field, and of course also biased by my own research. So in case you think there's something missing, I think it's also the perfect moment then in the discussion session to bring this up and we can discuss this all together. So my goal today is, so to say, to think about different questions that one can nicely connect to collider physics. So I start from the big astroparticle question, so to say. And this also what was said in the introduction. I mean, we are able to describe from the Big Bang to today the evolution of the universe. At least we have an idea. We know when protons formed, when, for example, BBN started. We know that we have the cosmic microwave background, that galaxies form, and then basically at some point we are here today. But still in this evolution of the universe, there are big questions. And one of the biggest questions is, of course, our own existence. So why is there more matter than antimatter? And this is on the one hand nicely quantified also by the CMB, but as I mentioned before, also via the Big Bang nucleosynthesis, the so-called deuterium bottleneck gives us a hint for this precise baryon symmetry. And thanks to these two measured values, we know what we have to target as a theorist to build models that end up with this observed baryon symmetry. Another, in my opinion, important open question of astroparticle physics is, of course, dark matter. We all know that there are different hints for the existence of dark matter. I put here one of the standard examples, namely the rotation curves of spiral galaxies. And we know that we would expect here in principle from the visible matter here this decrease when we go far from the radius of this visible matter. But what happens is that it stays constant. So also here, we see that the circular velocity, the constant circular velocity tells us that there has to be some thing which is non-visible that makes up this difference, and this which makes up this matter, what we call dark matter. The third open question, of course, not the only one. So this, as I said, a biased selection.
In fact.
Okay. So the third one is the nature of neutrinos. And so we know we have here the Nobel Prize in 2015 for the neutrino oscillations. And the neutrino oscillations tell us that the neutrinos have to have masses. But we also know that the standard model of particle physics cannot explain this. So also here an important open questions, and all of these three questions might be interconnected. And this is the goal of today, to think about how can colliders help us to move forward in these three questions. And also in the order that I just started, I want first to start with the baryon asymmetry, with the question, how can collider physics help? Because we need new physics to explain this baryon asymmetry. But why do we need this new physics? We need new physics because we know theoretically which conditions have to be fulfilled in order to create such a baryon asymmetry. The first condition, the most obvious, I guess, is the baryon number violation. And then the second and the third one, CNCP violation and the departure of thermal equilibrium. If we check with the standard model, we know that the first one is sufficiently realized in the standard model, namely through the Faraday processes. However, C and CP violation is not enough, and also the departure of thermal equilibrium is not enough, as we will see in a bit. So there has to be new physics to explain our own existence. And when we know this, as you also know, there's different, what I call terra baryogenesis incognita. There are, of course, different ideas. So there are different ideas what kind of models could explain theoretically such a baryon asymmetry. But the most pressing question here is, of course, which mechanism is really realized in nature, or are we completely wrong and we don't know the mechanism, or we haven't postulated this mechanism yet? And also here the question, what can collider tell us in this journey to find the baryon asymmetry mechanisms? In order to think how collider can help us, the best way is to think about theoretical strategies, how to get such a baryon asymmetry. And what helps us there are the three Sakharov conditions. So what we need for sure, as I said, C and CP violation is not enough in the standard model. So we need a new source of CP violation. Hence, looking for CP violation is always good in our journey. Secondly, we need B violation. I mentioned already before that we have these phalerons in the standard model that violate B plus L, but conserve B minus L. So here one could go what I call realization one, that we take these phalerons in order to make the baryon asymmetry without an additional source of baryon or lepton number, which would go into the way of Electroweak baryogenesis, for example. But there's the possibility that we have a new source of B and L violating, so other high-scale baryogenesis models. And here often what one is looking at is at heavy particles that fulfill the out of equilibrium condition by heavy particle decays. So similar, like, for example, in a freeze-in mechanism for dark matter. So we have often a right-handed neutrino that decays. And if the right-handed neutrino is heavier than the temperature, then we basically go out of equilibrium. The other option is a strong first-order phase transition. As I said, maybe combined with the phalerons, which was one of the initial ideas to have Electroweak baryogenesis. But what for both realizations is usually true, that we have always a competition. We have a competition of baryon asymmetry generation from a source of B violation, but we also have to be careful with so-called baryon asymmetry washout. So this is important because this we will see also in the course of the talk from time to time. So we always have this competition between generation of baryon asymmetry in combination with CP violation, and on the other hand, baryon asymmetry washout. And only if the asymmetry generation is the more dominant one, then we generate in the end the baryon asymmetry. So with these categorization, with the theoretical strategies in our mind, we can ask now ourselves, what are the experimental strategies to go into the right direction to know what generates the baryon asymmetry. And according to these strategies is one, to look for the out of equilibrium condition. It could be a strong first order phase transition, or for example, a heavy particle decay, which also brings us to the last bullet point, namely some new degrees of freedom from a specific UV complete model. So we can look for new particles, of course, at colliders. We can look for a new source of CP violation because we know we need more than we actually are currently knowing. And besides these phalerons, it could also be that there's a new source of baryon or lepton number violation that, of course, we can also look at collider searches. Okay, with these experimental strategies in mind, we go now through them and think about what is done so far and how can Collider help us in this quest for finding the right mechanism behind the baryon asymmetry. And as also, of course, it was nicely fitting, I was already smiling when it was said with the Higgs discovery in the introduction. This was a first guidance. The Higgs discovery, the 125 GeV Higgs, gave us already a hint what is possible or what is not possible for baryogenesis. And the reason is due to the mass of the 125 GeV Higgs, we know that within the standard model, we cannot get a strong first order phase transition. The Higgs is simply too heavy because we only get here this kind of crossover, but we don't get here this kind of barrier such that we get here this kind of bubble nucleation where we, for example, can, like with water, where we can do electroweak baryogenesis. So even if we would have a new source of CP violation, electroweak baryogenesis within the standard model would simply not work. Then we have at least two possibilities. First possibility is we simply change the potential of the Higgs and make it first order phase transition. Or another possibility is we think about out of equilibrium decays from heavy new particles, or of course, an alteration of these possibilities. So let's think first about the first order phase transition. And this is, so to say, the first what we want to look at. And I think what we should do, simply also historically, to think about what were the first thoughts to make electroweak baryogenesis beyond the standard model. And the prime example, of course, is, which I think many people hope for, the minimal supersymmetric standard model with a light stop. So beyond all solving the naturalist problem to have a dark matter particle, it would also have the potential to make a first order phase transition. However, lattice and other calculations tell us that the mass of the stop should be below 155 GeV. And then thanks to the LHC, we know, or we can basically here set limits. So this here is the stop mass, and this is Higgs into new physics. And here in blue, you see for the Higgs to vector boson, this here is the standard model. And if we would have a deviation to it, where we would lie here in this parameter plane. And this parameter space is here the allowed one with respect to the standard model. And we see here really for the stop, for the where we are really not allowed to be much larger, or we are not, we are getting basically pushed from the mass that we actually need to do a first order phase transition with a stop. Out of these reasons, then people were thinking, of course, okay, how can we do to add other degrees of freedom to change the potential, to make it first order phase transition? So there's, of course, a lot of literature. Not all of the literature I put here is, of course, there. So there's more. But the general difficulties are first constraints from EDMs. And on the other hand, of course, collider constraints, as here with respect, we have the full precise Higgs physics. So here we need to make sure that we don't alter really all the precise Higgs observables. Then, of course, people think about how can we describe this in a more effective way. So this is what is done here. So this is the Higgs potential with higher dimensional operators. And if we would now rewrite it and rewrite here the correction to the triple Higgs coupling, the lambda 3 over the lambda standard model, we could get here this delta. So this delta is the correction to the triple Higgs coupling coming from higher dimensional operators in the Higgs potential. And what we see here in the plot, so this is lambda, so this is here the scale of these operators, and this delta is the correction on the triple Higgs coupling. And you see now here what here in these lines, what is the general possibility for the power 4 terms, where we could get a correction, or what could be the possible correction to the triple Higgs coupling. However, when we want to have a first order phase transition, you see that generally you get a positive correction. So this means larger triple Higgs couplings are usually associated with the first order phase transition, while smaller with a second order phase transition. So then the question is, how can we check this? So we want to check the triple Higgs coupling, and here the collider probe is, for example, the double Higgs production. So we have here 2 Higgs in the final state, here the box diagram, here the triangle diagram, and what is important that these can have certain destructive interference effects. So what people looked at is, on the one hand, here, for example, we have a double Higgs invariant mass, and here the normal distribution. So here this red dashed line is the normal distribution if the triple Higgs coupling would be from the standard model. And you see here, with respect to different values, it can be negative when it shifts here a little bit to the left, or here to the right when it's positive. So you see the idea is here, so to say, to check what kind, how to narrow down the possibilities by measuring the triple Higgs coupling, which is of course extremely difficult. Here, another example. So this was, so to say, really based on the effective operators I showed you before. Here people introduced really a scalar field. Here you see the mass range of this additional scalar field, a light scalar field, also to alter the Higgs potential. So this is a more UV complete model realization. And here this is the mixing of the new scalar and the Higgs. And you see here also the extrapolated range of here a high energy LHC. So you see here that we can of course shift, and this is, so to say, the potential where I think, yeah, the future colliders or the future collider searches hopefully can really make an impact to get further to this question about the first order phase transition. What is interesting in this context, and I think is also currently a lot of discussed, is of course the interplay with gravitational wave physics. So what I want to point out is here a paper by Michael Kalla and Jamal Munadini et al. So also here you see the same idea. Usually one puts additional operators and one sees how can I constrain them. So you see here, this is the 6-dimensional and the 8-dimensional. So this is here the effective coupling on the Y and the X axis. What does the color mean? So here in the green area, you get a strong first order phase transition. So here the 2 different colors are not really important, but what is important is here the dark green. This is the reach of LISA. And on the other hand, here this range, the dashed range, would be the range of the FCC. So you see also here there is a nice interplay that, yeah, if one would see something, one might expect something at the other experiment. And here you see also the same, just the effective operators translated into effective couplings. Again, the triple Higgs coupling and the quartic coupling. And you see here just in a different mass plane. While here this gray area would be out of experimental reach. So I think this is currently really exciting to, try to get from cosmology or from elementary particle physics to try together to really think how do we get or can we get a first order phase transition still with the known physics that we're having. So if we, of course, want to think about other possibilities, so one can, of course, these were examples from, I would say, the conservative approach to change the Higgs potential. But of course, there are many new ideas to have a baryogenesis or a dark first order phase transition, or for example, to have QCD baryogenesis. So this is just one example for some other possibility that we can have, which might be more exotic than the usual approach of changing the Higgs potential with a scalar field. The idea here in this QCD baryogenesis is that we do baryogenesis with a QCD phase transition. And this sounds first a bit problematic because we know the QCD phase transition is not first order. So the idea, or what one knows, if the QCD, or if the number of massless fermions is larger than 3, then the QCD confinement proceeds via strong first order phase transition. So this is a statement that was already done extremely early in the literature. And what people try to do now is simply to change again either the QCD, to change the Higgs potential in that way that QCD confinement with a first order phase transition happens before the electroweak symmetry breaking in order to have the massless fermion to have a first order phase transition, then we would get here into a deconfined area and then to the normal one, what we know is the confined one that we are actually normal. So this is, so to say, one idea. So here you would change by this the strong first order phase transition. And then the idea in this paper was to have already an axion as a certain CP source. And why do I mention this? Because I had on my slide also not only a strong first order phase transition that we can probe, but of course also new degrees of freedom. And what is postulated here, of course, we need something to change the Higgs potential. So we have here new light scalar particles. You see they are around really 5 to 30 GeV. And they have here a small mixing or a small branching ratio. And you can see, you can measure this or you can constrain this already with Opal and Lep, but a potential Higgs or Z factory might reach even lower in order to rule this out or to really discover this kind of light states that one would need in order basically to do such a QCD baryogenesis model as suggested here in these papers. So I said first order phase transition, but as we also know, we need also CP violation. So the question is, how can we probe CP violation? Of course, here I can also only pick something out, but cannot talk about everything. But what people did pretty recently is they looked into possible 6-dimensional operators in what they call universal theory. So you see, you have here the different operators that you can have that can describe the electric dipole moments. And they confronted this with the LHC. And usually, of course, these are extremely suppressed because they are loop contributions. But what they try to show is if you look into the correlation of two different ones, that then here in red, the electric dipole moments can also say something with quite specific. While you see here in this correlation, the LHC here is still has a larger uncertainty, but can reach in the future here in blue also some kind of very small uncertainty, which is then nice to confront with electric dipole moments. So here the idea, so to say, usually one often takes only one operator at a time. And in this work, what they wanted to show is, okay, if we take 2 operators at a time, what happens then? And this is basically what they try to point out here. Then basically the picture looks a little bit different. So we have the first order phase transition, some out of equilibrium. I mentioned already light new degrees of freedom. I mentioned CP violation, but last but not least, the last one is probing B-L violation. As I mentioned before, in principle, to be precise, we have non-perturbative effects in the standard model, the sphalerons that give us B-L violation, B plus L violation. But of course, now the question is, do we have additional sources of B or L violation? How does it look like? Because for now, on a quantum level, B and L is just an accidental symmetry. So I want to start with the baryon number violation, and then in the second step, go to the Lepton number violation, which bridges also to the second question, to neutrino physics. But first, let's stay with the baryon number violation. And in principle, what one can do is, or what kind of possibilities we can have a look into different effective operators, either the one that violate baryon number in terms of terms of 1, which are highly constrained. The constraints come from proton decay. But the another possibility is delta B equals 2. And this, I think, quite recently got quite some interest because of the future experimental prospects of these N-bar oscillations. What are N-bar oscillations? So in principle, the idea is that we have neutron, anti-neutron oscillations, and these one, like neutral meson oscillations, one expects one could measure them. Why? Yeah, no, you have a neutral state which oscillates, so why not? So let's check this. And these would violate baryon number in terms of 2. And you can write this down here in this effective operator, as this is 9-dimensional. This scale is here suppressed with lambda to the 5. And you see now here the future sensitivity. So you have here in the year 2030 and later, you will see that we will get really some new experimental possibilities to test the scale possibly of new physics or also NMR oscillations. So the future sensitivity will be 10 to the 10 seconds, which then, if we do a naive estimate, would point us to a new physics scale above 10 to the 6 GeV, that, so to say, we would reach or could exclude new physics to a scale to 10 to the 6 GeV would be quite amazing. So now the question is now, how does the Collider physics come in now? And B, how can we connect this now to baryogenesis? And this I want to show here. So as I mentioned in the beginning, we have, in order to create a baryon asymmetry, we have the baryon asymmetry washout and the baryon asymmetry generation. And this baryon asymmetry washout, if we have here no CP violation, could be exactly such kind of an operator. So an operator that we could potentially measure at antineutron oscillations. And as we know, when the rate of a process is larger than Hubble, then we can say the process is highly efficient. And what we did here is to estimate when would be this process, the washout, highly efficient, which would imply that we could not generate this kind of baryon asymmetry because it would wash out again a pre-existing baryon asymmetry. So the idea is now, if we would measure neutron-antineutron oscillations, what can we say of the validity of high-scale baryogenesis models? This you can see here. This is now the potential scale of this kind of operator. And this here is the temperature until which the washout would be effective. And you see now here, these are the future, current and future, the future limits. And you see now above this, the rate, the washout is highly effective. And below this, there would be still room for new asymmetry generation. So this line tells us above which scale is this washout highly effective. Below, the washout is not so effective anymore. And you see now that while the LHC reaches already the mass scales of particles to the TeV-ish and 10 TeV-ish scale, of course, here's room also for future colliders. So basically, if we would measure something at antineutron oscillations, then it would be interesting to see what would this imply here for the LHC physics. Of course, this was now just based on effective operator analysis, and this is also why we wanted to have a look, how does this look better or more precisely in a UV complete model. So if we want to look now into this operator, we basically have two possibilities. So one I call topology 1, which also was looked at by Christophe Grosjean. And the second one is here topology, which is also motivated from gut physics. And what we wanted to have a look now is, okay, if we now would measure neutron-antineutron oscillations and we make now a simplified model, so we go beyond the naive EFT analysis, what would it tell us for the different interplay of different observables? Because you have to keep in mind, of course, baryon and neutron-antineutron oscillations are a complete different scale as the LHC. And of course, here we have to be careful that we carefully compare the limits. This you see now here. So if I go back, so this here is the interaction that we want to look at. And we have here now one of the particles, so here, which I call XUD, which can be a diquark. And you see we have two different diquarks in this model, which are around the same mass range. And we said also here the couplings equal. So we simply want to see what is the reach of the different experiments and where would we end up with the right baryon asymmetry. So you see the right baryon asymmetry would be only possible for very high particle masses, while here the LHC or also the NN-bar constraints could only constrain to a much lower scale. This also makes sense of what I've said previously. If we would measure something at a low scale, and the scales have not a huge hierarchy, it would imply such a huge washout that we cannot generate here the right baryon asymmetry. this also makes sense here if I compare this with the EFT. Now, if I change the hierarchy, so now you will see I change now the hierarchy of these particles. So I have a very heavy one and a light one. So you see here, this is what I vary in the TV range. Then it looks different because now I have this huge hierarchy, which I have to be careful when I describe it with the effective operator approach. So you see now this XDD is very heavy. The XUD are here, the diquarks in the TV range. Here in the red lines are the right baryon asymmetry. And you see now here's a nice interplay between the LHC or possible future colliders and the antineutron oscillations. So it would basically hint us if we would see something in antineutron oscillations and such a model or this model could generate the baryon asymmetry, then we would also want to see or expect to see something at the LHC or at the future colliders. And I think here this interplay can be extremely powerful to really set limits or to see what kind of models can actually give us the baryon asymmetry. So I think here this is maybe, I don't know if there are any questions, maybe a good point before I jump to the part that is also more connected to the question with respect to neutrino physics. So in case there are any questions, I'm happy to answer them.
I don't see any raised hand.
Okay, so then, as I said, you can of course also ask later on.
At the end. Okay, thank you.
Okay, so now this was, so to say, more the baryogenesis part. But of course, we know we can also have something what we call leptogenesis, where we have lepton number violation. So what is leptogenesis? Yeah, we have here the similar picture with the only part that we create first a lepton asymmetry. We have the sphalerons that generate a baryon asymmetry, and here a possible tight link to neutrino physics. So why is lepton number violation interesting? And especially now with respect also to leptogenesis, because lepton number violation could also be tightly connected to the nature of neutrinos. That is one of the other big questions that we want to answer. As I mentioned already before, lepton number is in principle, if I would add a right-handed neutrino to the standard model, no accidental symmetry anymore on a classical level. So it would mean that I can similarly also write down this kind of Majorana mass term. However, this Majorana mass term cannot be written down in the standard model. And the reason for this, or the reason then, is that we need really some higher dimensional operator. We hear this 5-dimensional operator, lepton, lepton, Higgs, Higgs, which generates a Majorana mass. And important, this would be lepton number violating. So this basically means if you think about a right-handed neutrino, depending on which philosophy you're having, but it could also quite naturally or quite consequently imply that it's natural to look for some lepton number violation. And of course, lepton number violation is interesting also with respect to leptogenesis and the idea to generate a baryon asymmetry. So what can we do? I said we can do leptogenesis and connect this here to this so-called Weinberg operator, lepton number violating operator. And we have two different possibilities, basically. On the one hand, the high-scale leptogenesis, and on the other hand, the one via oscillations. What is the difference? The crucial bit is now, if we want to have a tight connection to light neutrinos, we are, of course, limited by the neutrino masses. And you have now two philosophies. So either you have, or let's start here, either you have a heavy right-handed neutrino, which would be the resonant, the usual high-scale leptogenesis. But then in order to get the light neutrino masses, you would have a tiny coupling, which is difficult to measure. On the other hand, if we want to have, for example, here in the GeV range, then we could have couplings that are again then in a more accessible region. So now we have here the possibilities to probe high-scale leptogenesis, and there are many, many different possibilities. And I just listed here some, so there's also a nice review where one can have a look at. But of course here, if I have really exact UV complete models, I can, of course, look, for example, to specific LHC signatures, like the same sign dilepton final states. I can look for new scalars if I have a seesaw mechanism, or other model-specific signatures that I can look for at colliders. So, but the crucial bit is, and that this Weinberg operator that I mentioned before is not necessarily the only option to generate Lepton number, and also to generate Lepton number violation, and also to generate neutrino masses. So far I've only talked here about the 5-dimensional one, but in principle there are other Lepton number violating operators at odd mass dimension. So here the 5, the 7, or the 9-dimensional one. And what is now interesting is how can we probe this? And if we look here as an example to this 9-dimensional one, we have different possibilities. We can look here to rare meson decays. You see, I can look here if this operator is exactly the one that would give us neutrinoless double beta decay. But also, if you look here, it also is here this 2 same sign lepton, 2 jets, and no missing energy signature at colliders. So here we can have a tight interconnection between the different observables. And what we want to do now is to see what can colliders and also in close crosslink, for example, with neutrinoless double beta decay tell us. And in principle, the LHC, if it would measure Lepton number violation, could tell us actually something extremely dramatic, because it could tell us basically that certain high-scale baryogenesis models might be falsifiable. This is, of course, a strong statement, and of course, caveats apply. One has to be careful. So I don't want to, one has, of course, to be careful. But the message is the following: as you have seen, this is one of a UV complete realization here with generic way of this 9-dimensional operator with 2 same sign leptons, 2 jets, and without any missing energy. And what we could show is that we can get to this washout. Remember, this gives us an idea. If I have a higher, at a high scale, I created a baryon asymmetry, but now at low scale, I would measure these processes, and there's no CP violation included, and I would measure these processes at TV scale. And what I would get from the LHC, I would get the LHC cross-section, and I would get here the resonant mass mx. So then I can plot this, and what you see now here, and also when you look here at this expression, that as soon as you are in a realistic cross-section that you could measure at the LHC, the washout would be so strong that it has the potential to falsify high-scale baryogenesis models. Hence, Lepton number violation has not only a strong impact with respect to what we want to know if the neutrino is Dirac or Majorana, but could also tell us something incredibly strong about leptogenesis or baryogenesis models. Of course, as I mentioned before, the LHC is not the only experiment that can tell us something about these interactions. Of course, it's important to cross-link it with other experiments. And you see here, if I now integrate this out, which should here be this blob, you see I get here the 9-dimensional operator in neutrinoless double beta decay. And in principle, what we could do here, we could make a similar statement. If we would measure neutrinoless double beta decay, and it would be realized of one of these higher dimensional operator and not the Weinberg operator, this is the crucial bit. It has to be something 7-dimensional or beyond. Again, the washout of this TV scale interaction would be so strong that it would wash out any asymmetry that would be generated before. Or in more detail, so you see here, now this is the energy scale above which the washout would be strong, so at which this condition would be applied. So this is here, this lower bound. And this is here from a potential measurement, the validity of the EFT. So we know that in this dark region, we have a large washout. This is the current, and this is the future limits. You would see now, if I would now measure this 9-dimensional operator at the LHC, it would be here, would be able to wash out everything down to the Electroweak scale. So even if we would have here generated previously a baryon asymmetry, these processes would be so strong to wipe out everything down to the Electroweak scale that there's no room to create again an asymmetry. And this is also why this applies to these higher dimension operators, which is in contrast here to the Weinberg operator, because you see here you have much more space to generate again a baryon asymmetry. So now with this nice interconnection, we wanted to see now how can we really connect in a simplified model study, this TV scale Lepton number violation. Because again, one has to be careful, neutrinos double beta decay is at a much lower scale, of course, than the LHC. And there we have to be careful if we want to compare results from an EFT analysis with a UV analysis. So what you see here is now a UV realization of such a simplified model of TV scale Lepton number violation. So we have here a scalar singlet coupling to the quarks. We have here this, again, the scalar singlet and a Majorana fermion. And you see here, this is Lepton number violating. This is not Lepton number violating. And if I would now, so these are the TV scale Lepton number violating interactions. And if I would integrate this now out, I would exactly get here this 9-dimensional operator, what I was talking before. One side remark, we would also get a contribution to the neutrino mass, of course, via loops. However, this depends here again on this coupling, which is independent in this case of here really the Lepton number violating interaction. So here there's not a direct link, but of course these processes can also again give via loops contributions. And in order now, as I mentioned always before, we imagine we have a symmetry generated at a high scale, and we want to know what does TV scale Lepton number violating actions tell us that we could potentially measure at colliders or neutrinos double beta decay. But in order to model this now more precisely, what we did is we included this high scale baryogenesis generation via the standard thermal leptogenesis. So this is here the typical right-handed neutrino. And these interactions on top of it that give us the TV scale Lepton number violation. And the question now is, can TV scale Lepton number violation, potentially seen at the colliders, LHC future colliders, and or neutrinos double beta decay, destroy a lepton asymmetry which was previously generated by right-handed neutrino standard thermal leptogenesis? What one needs to do here is to take into account all the different processes. So you see here, one can calculate the leptogenesis. We have here in bold the usual processes of the standard thermal leptogenesis scenario. And here in small or in fine print, the additional processes. And you see they only contribute, as I mentioned always before, to the washout. We can solve this, and then we can see what kind of baryon asymmetry do we get. And this you see here. So this is now the area where we do not get the right baryon asymmetry, we are below. So we would basically falsify, or we could, these processes could destroy again a high scale generated asymmetry. And here GL and GQ are exactly here, these couplings in our model. Now we want to confront this with colliders, with collider physics. And you see now here, with these couplings, I can either generate here this kind of G channel to same sign leptons to jets, as I mentioned before, or here this resonant decay. Depending on the mass hierarchy of this particle S and F, we can get different mass hierarchies, and the most contribution comes when here we have this resonant production of the S. So we did here the signal generation, background standard model, the signal to background discrimination, in order to get really limits or constraints from the LHC. The same, similarly, we did with neutrinos double beta decay. So here, as I mentioned before, we have to be careful now. This is the UV model. We have to integrate it out to a lower dimension. We also have to take into account that we have here at some point pions, and then we can relate the half-life, which is measured from neutrinos double beta decay here with the Wilson coefficient and the parameters of the model. We put everything together, and what do we get is the following. So this here is the lambda. So this lambda depends now on the mass S and F of the new particles, as you see here. And this is the GF, the effective coupling. In this case, we set them equal. Important on these three plots is that while GL and GQ are the same, we have a different mass hierarchy of the different particles, S and F. And this is now the important point. When we have the mass hierarchy, that this is, for example, not resonantly produced, you see here that neutrinos double beta decay, current and future, is stronger than collider physics. However, with a different mass hierarchy, the picture dramatically changes. So you really see here, depending on the model or depending on the mass hierarchy, one or the other experiment is the more stringent one in this case. So this is why it's really important to put both together. And this could also tell us something, of course, about the leptogenesis scenario. And this we see here. So here we see again the couplings GQ and GL, and I showed you before the red area. So this is again the same plot, but now I overlaid the constraints from neutrinos double beta decay and from collider physics. Again, the same color coding: in green neutrinos double beta decay, in blue collider physics. And here you might wonder what the grayish area is. This is simply, if you look directly, for example, for the S, direct production, so this is the gray, while here this is the true lepton number violating signal in blue. And again, two main conclusions. A, we see that really there's a competition depending on the mass hierarchy that we have seen in the previous plots. What is the more stringent one? And number two, you really see, how should I interpret it now, when the red area and the blue or green area is on top of it, it really means if I would now measure at the future collider or neutrinos double beta decay experiment lepton number violation, it would lie in the area where I said before we could actually falsify or put under tension standard thermal leptogenesis scenarios. And so to say, this is really now done in a really UV complete model analysis to stress that the previous work that was done independently really works out in this kind of UV model. And I think this again nicely demonstrates the interplay and also really the crucial future experiments on both sides to really get further here. Yeah, there is maybe a question.
Eccola qua. Verranno settimana, ha detto. Poi lo chiamo.
Roberto, do you have a question or just no? No question.
Okay, just to make sure.
Exactly. Okay. Sorry.
Okay, and of course, just to say, I mean, as I said, to be fair, I should also, this is so to say only a lepton number violation. But of course, if we think about neutrino physics, I also want to stress here that of course also here collider physics gives us a lot of input. So as I said, usually what one thinks, we have maybe right-handed neutrinos in our model. And you see here on the y-axis the mixing, and on the x-axis the mass of the sterile neutrino. And you also see we have here a plethora of different, depending on the mass range. I mean, really see it's a huge mass range, 10 to the minus 9 to 10 to the 3 to the 4, where of course also here the ATLAS and CMS experiment gives us a lot of input. And here the future projections, they really see that there are a lot of competitive results and also at different mass ranges. Okay, so I think here is also maybe a good point in case there are any questions. Otherwise, I would come to the last part of my talk. But are there any questions?
No, it seems they wait. They're waiting for your conclusion.
Okay, so then in the last remaining minutes, of course, I should, besides neutrino physics and the baryon of course, mention dark matter. As I said, it's also one of the pressing questions that we're having. And then let's ask, what is the status of the WIMP? Here, I don't know, depends what you read. Matros are dead, WIMPs are no-show, say hello to Sims. The WIMP miracle hope for dark matter is dead. And maybe here the more precise, of course, from nature, last chance for WIMPs. Physicists launch an all-out hunt for dark matter candidate. Yeah, what is the status about the WIMP? Of course, we have no observation on so far with the LHC direct or indirect detections, but the reasons, of course, can be manifold. Of course, it could be that dark matter is simply something else than a WIMP, but it could also simply be that we have a more complex WIMP, that there are neglected important effects in our calculations, that our theoretical prediction is wrong, that there's another mechanism, freeze out versus freeze in. We have a much lighter, heavier dark matter candidate, FIMP versus SIMP, or a completely different type, primordial black holes, axions, etc., etc. And I guess I missed other reasons. So here you can add your favorite one, why we haven't seen WIMPs yet. So what I want to stress here is now, if we stay first in this WIMP picture, that in my opinion, also the WIMP by far is not yet dead. And the reason for this is also that we might have also in the interplay with collider physics, maybe forgotten some or not taken into account important effects as much as maybe are needed in some parts of the parameter space. Because, for example, if we calculate the relic abundance, we know that the relic abundance is roughly indirect proportional to the cross-section. And what we also know, thanks to Griest and Seckel, we can also have something like correlation, meaning if the mass difference of the dark matter particle here and another particle are close enough, then correlation can occur. And then we can put everything together, and we see here this in the end, whatever parameter space, usually a small thin strip which constrains the parameter space. However, what we also know is that there are other effects. So usually these naive calculations, micromic, Stark, SUSY, METDM, super ISO relic, usually take, not in all models, but usually take the tree level into account. However, we know that higher order corrections can have an effect. We also know since long that Sommerfeld enhancement can have an effect, and where a lot of focus in the last years also was in that bound state formation can actually have an effect. How? The idea of bound state formation is similarly like when you have Sommerfeld enhancement. Imagine you have some two, for example, an electron and a positron, some particles that of whatever feel an attraction to each other. Then this attraction would give us here the Sommerfeld enhancement. But of course, if the attraction is so big and then they radiate some kind of binding energy, they could also form a bound state. And if this bound state now decays again into here these mediator particles, then they can deplete also here the particles that go into the dark matter calculation. So this means if the bound states form and doesn't go to the back reaction, but decays into constituent part, not in constituent, but in mediator particles, then what effectively will happen that we get an effective annihilation channel on top of it. And this can have huge effects, as you see here. So this is just one example. So also here, this is done in different models and different realizations. But just to give you a glimpse into this effect, so this delta M is the mass difference between the dark matter particle and the co-annihilating particle. So this is delta M, and this is the dark matter mass. And you see now here in gray, this would be the naive calculation if I would take a dark matter tool out of the box. However, if I would also introduce or include bound state formation and Sommerfeld effect here, in this case, into a colored correlating scenario, of course, otherwise I wouldn't have the gluon, I get here this line instead. And if I include also here the Higgs exchange for a certain coupling, then this effect would be even bigger. So bottom line, depending on the model, I should think if these effects can have an impact on my prediction of the dark matter abundance and also here the mass differences. Why is this important? It is relevant here out of different reasons. So we see now we shift on the one hand the absolute dark matter mass to the right. This is interesting for indirect detection. On the other hand, we shift the mass differences to larger values. This is interesting for collider searches because what we were maybe looking before at, and we were thinking we were excluding or the parameter space would be still alive, is maybe not because we go from soft signatures to multi or monojet signatures. So this is why this is relevant, and of course also to have a precise calculation. Of course, we also want to have simply done good work. So what we are currently doing is to put this into more context. So to say, currently with the T-channel working group effort, to think how do the results also with respect to collider physics change when we include these non-perturbative effects. And here we used one of the simplified T-gen models here with the UR model. And what you see is that on the one hand, from this coupling, I get here the correlating, but I also get here the annihilation of this colored particle. And this is exactly the one that is subject to these huge non-perturbative effects. So you see here again a similar plot. This is the dark matter mass, this is the mass difference. And what you see now here in GDM is the lower limit on the GDM here in the model, such that I don't overproduce dark matter. And you see now that I can get a certain limit such that I then, and these limits here come from direct detection, such that I know, okay, what would I expect, for example, in collider searches or to confront it with collider searches. But of course, now you have to ask yourself, okay, I talked now about the tree level calculation, I talked about non-perturbative effects, but okay, how does GDM now change? This you see here in this plot. So what is plotted is here in this color code is the GDM that I would get when I take bound state formation into account from the experimental data. And this, if I would take over the perturbative one. And you see here, you get a huge change when the color is very dark. And you see here, especially in this area, you get a huge change in the GDM. And what does this then imply? This does then imply here, this is again the same range. You see now here, what we took into account is the relic density. We took the direct detection and also collider data. And now you see, depending on what calculation I rely on, only the perturbative one in green or bound state formation, you see the parameter space actually opens up. What is the reason for it? The reason for it, as you have seen, I can get now smaller couplings. So I could get the relic abundance, or I would not overproduce dark matter with a different coupling, and this coupling is then not yet constrained, and hence the parameter space opens up. And I think this is also, you see, for example, here this cut, this is, for example, here what comes from the monojet searches, which basically constrains here this part. But there's still parameter space open that basically is interesting to look at in the future. So the question is, but still, why haven't we seen dark matter yet? And as I just said, we can now go to the high energy frontier, so basically to higher energy to look for higher dark matter mass particles, as I've motivated just right now. But of course, we should also not neglect that the long lifetime frontier is also growing. So with Phaser, SHIP, Codex B, and Matusla. And then, of course, gives us the possibility to think about if dark matter is maybe not weakly, but feebly interacting. So this is then the example for the freeze-in mechanism. And yeah, in contrast to the freeze-out mechanism, what we have here is simply that dark matter was not in thermal equilibrium or before, but the mother particle or the parent particle. And only when the parent particle here decays, F is here the parent particle, L is a lepton, and S the dark matter particle. Through the decay, we produce our dark matter. And what we will see then is here that the relic abundance now is not indirectly proportional to the cross-section, but goes with the rate. And of course, this also opens up a lot of connection to colliders. And this is why we looked into LHC friendly freeze-in models to see what can the LHC tell us with this respect. So what you see here is the Lagrangian, where we have here the scalar singlet, which is of course a dark matter particle, and we have here vector-like SU2 singlet fermion, which I call here F. And then we can get exactly this interaction, what I've mentioned before. So the dark matter particle, a standard model particle, and F, the parent particle. And if I look into the quantum numbers, I can have either leptonic or hadronic, or the quarks. And then I have also here the free parameters, which is S, the dark matter particle, and F, the parent particle, and here the Yukawa coupling. So now let's confront this with the LHC searches. And here I can have different collider constraints. On the one hand, if these particles are very long-lived, I will see a track through all my detector. So it's the heavy stable charged particle searches. If they are medium long-lived, I can get here this disappearing track where they simply decay and then I don't see anything anymore later on. Or I can get something like displaced vertices or displaced lepton searches that are interesting in this context. So if we then put everything together, so you see, of course, we have different free parameters. MS, the dark matter mass, is of course a free parameter, but thanks to the diamond alpha forest, we know what is the lower limit. So this is, so to say, here the dashed lines are the lower limits, and then we open up for other dark matter masses. And you see here now the constraints that are actually already given from the LHC by either the R hadron searches, the displaced lepton searches, or the disappearing track searches. So now what you see here, and you might wonder, okay, why do I change now this TR, the reheating temperature? And this is what I want to motivate now, that even there unexpected, at least for me in the beginning, unexpected connections can be drawn if one looks a little bit closer. Because let us think again, how can we calculate the relic abundance, or how can I make a connection of the relic abundance and the lifetime? So here in red, you see our free parameters, or the the parameters that I measure at the LHC, the lifetime and the particle mass MF. And here MS is the mass of the dark matter particle. As I said, it has a lower constraint from the diamond alpha forest. And we have the relic abundance. So if we now want to say we want to have the relic abundance, then we can, and we have a lower limit on the dark matter mass, we can ask ourselves what would be the corresponding reheating temperature. And even in case it's not made up all of, or the S doesn't make up all of dark matter, it is still a smaller, we would have a smaller reheating temperature. Basically, we get, so to say, an upper bound on the reheating temperature. And this is what you see here now, that depending on the reheating temperature, I have different predictions of this curve. So also here, in case we would once manage to have this kind of resolution at colliders, it might, and we would measure not only some particle MS and the MF particle, or even the lower limit MS, we could get a hint on actually the reheating temperature of our universe. So as you see, there's often unexpected tight connections about astroparticle physics and collider physics, and of course other experiments, but as I want to mention here because we look into collider physics. And I think, it's extremely interesting to see. And here also the future prospects, what can we do in the future? And you see here in dashed, I mean, these are the corresponding high-Lumi extrapolations. And what you can see here is, so to say, the reheating temperature for 160 GeV, and at some point we would really cover here everything. Only this little bit would maybe survive. So this is, I think, very interesting. And of course, there are more and more extensions, and I don't have the time to go all into it, and I think it's also too much. But what I want to motivate is, of course, we can also connect this again with neutrino physics. There was even work by looking into displaced vertices or, stop particle decays to make connections to maybe a different cosmological history. So I think also this is really an interesting possibility to have this, again, the link from cosmology to collider physics. And of course, if we assume we don't have weakly or feebly interacting, dark matter might be strongly interacting. So we enter then the idea of composite dark matter, QCD-like dark sectors, where of course we also can have a rich, strongly interacting dark sector, similar maybe to the standard model, but in the dark. And then depending on the QCD scale, we could get also different possibilities like dark conium, dark mesons, or quarks, and also a rich new signatures at the LHC. And for example, here, this I found quite nice, I just stumbled over it, that also here already for phaser, for example, just recently people proposed that even these kind of quark signals that are basically, if there is no lighter constituent particles and this color string cannot break, you get these quarks, that they basically can also maybe even be measured at phaser. So I think, we have a lot of possibilities. Of course, what I've mentioned is not everything yet, but of course I don't have the time to discuss everything. And with this, I also want to conclude but the question is, what shall I conclude? What do we know? And I think what we know is that astroparticle physics connects the early universe cosmology really nicely with elementary particle physics, with all our open questions that we're having, dark matter, baryon asymmetry, neutrinos. We have many ideas and also great prospects with future collider searches to also contribute in a complementary way to other experiments. As I said, neutrinos double beta decay, neutrino oscillations, direct and indirect detection. And I think we have a bright future ahead at all frontiers. But of course, at some point, we want to see a hint. And I hope that one of them in the future will give us the decisive hint that we know where we looked in the right direction or not. And yeah, with this, I want to thank you for your attention. And yeah, in case you have any questions, of course, feel free to ask them.
Thank you, Julia. Thank you very much. It was really a pleasure to hear all this information and hints on the 3 subjects that you cover. I didn't want to interrupt. Actually, I tried, but I was not successful. We are a little bit out of time. No, it's okay. It's okay because we have also time for discussion. So it's okay that you finished and you gave us all of the information that you wanted. So it's time for questions, please. If there are questions. Don't be shy. Roberto.
Hi. I actually a naive question. We sometimes discuss these models of Lepton number violation, even Lepton flavor violation at colliders, and I was wondering how robust are the statements that we make when we claim that some number is actually violated. What I mean is that if you see an excess in same sign by leptons, for sure you have seen something new, and that's no doubt about it. But what kind of assumptions are we making when we claim that that's a lepton number violation, for instance? The reason why I doubt about it is that colliders are very messy, and after all, you may have leptons of the opposite charge, if you like, that would compensate for it, that has gone undetected or anywhere you like. So I know we make that statement a lot, but now that you exposed a little bit of the signatures, I started to ask myself, are we really sure that if we see that signal, we can really talk about Lepton number violation, or maybe we need to at least qualify it a little bit?
Exactly, very, very good. And I think this is also what I usually always stress, because it's also really important to me. This is also why here I usually stress without missing energy, because of course, I mean, one thing is, of course, what we want to make sure is that we are really Lepton number violating, right? So basically, even if we would have neutrinos in the game, they could balance the Lepton number. So what we want to have is really a signal without any missing energy. And this is also why here this limit is, not so, I mean, this I have to admit is old data. I'm not sure if it was updated, but this was it. What the search that we have used here was really a dedicated search without missing energy. So basically, you're absolutely right. If I have searches that include some missing energy, then of course I cannot make a full conclusive statement if there may be some neutrinos that I missed and that balance, so to say, here the Lepton number. Additionally, what you also said, I mean, I mentioned it here, is of course true that a big point can be the charge misidentification in the whole game. Then of course I also don't know if it's Lepton number violating or not. So here also, for example, here we took this into account in our analysis to include for these possible, what we treated as background, so charge misidentifications or jet fakes from leptons, where we could basically assume we are Lepton number violating, where we're actually not. And so what I try to say is that, of course, one has to be careful with these statements when picking the analysis. And of course, in the whole game, I would basically say this is also why it is so good to have this complementarity. To really, if we have a signal at the LHC where we would say it's Lepton number violating, to really make sure that everything is robust and it's at around the TeV scale, I would also assume to maybe see in other experiments some complementary probes. This is basically, yeah, what I would say. So I hope I answered your question. So basically, yes, one has to be
yes,
really
yes,
careful.
yes. Thank you very much.
The other Roberto.
Yes, it's really a curiosity. It's about these neutron oscillations, which are clearly not easy to be detected experimentally, and we could be in a situation where the oscillation time is so low that is essentially undetectable. I mean, would the oscillation of other neutral baryons do the job? I mean, suppose we are in a situation where baryon number violation is related to other neutral baryon. Is something which is reasonable with our current model of the early universe, or you really need the neutrons to oscillate? It's a question for an experimentalist, so it's really a curiosity.
No, I think you're absolutely right. So I think this is another example where you have baryon or here B mesons oscillating. So in principle here, if I go to this one, I mean, this is the example of the neutron antineutron oscillation. So maybe also here first we have here the free one or the bound one, and as we said, of course it's difficult. So here with the free ones we have really a neutron source and we try to measure it, while here in the bound one we have a bound target where we want to see it. Of course now one has to compare with different. So bottom line, you can of course also look into other meson oscillations, like where do I have it? Meson, yeah, meson oscillations. There we go. To some other meson oscillations where I could also potentially have some baryon number violating signal. So in principle, all these things together help, of course. The neutron antineutron here is just because we will get also here a huge sensitivity increase, and is really a direct probe of baryon number violation in terms of 2. But of course, you're absolutely right that other mesons oscillations could also give us a limit on this.
Okay, thanks.
Aldo.
I have a non-expert question, sorry. So
no, come on.
It is about the use of red-ended neutrinos in leptogenesis, because there are people that use basically induce charge parity breaking in order to have leptogenesis from the neutrinos. And my question is how that is consistent with collider data. For example, is there any clash with precision bounds or Higgs physics?
Okay, I'm not exactly sure what you mean with a charge parity breaking. So
in which
okay,
this,
so
this extra right-handed neutrino oscillate and violate.
Okay, so you would basically say if, okay, so basically you would basically your question is, okay, if I assume now I have a certain CP symmetry here, if this would be in conflict, for example, with certain whatever Higgs measurements at the LHC or whatever.
Or any other collider hints from that.
Very good point. I mean, in principle, these, okay, let me think. I would say in principle not, but the question is, of course, why? And I mean, first, usually what one needs here for the CP is already very tiny. So I mean, usually in Leptogenesis models, you have a CP symmetry of around 10 to the -6 or so. So in principle, it's not a huge symmetry. This is one thing. Then secondly, of course, now we can think about it. I have to admit, I've never really thought about it, but if I now have the Higgs and here I would get some contributions maybe to the Higgs.
Well, probably they are too heavy to have any.
Yeah, I guess this is, I mean, this is the point. I mean, we have usually the right-handed neutrinos around 10 to the 13 GeV, and if you then have them in the loop, I guess it's so suppressed that it's tiny. The other question is, of course, if we think what I didn't mention is if we have, or what I did not mention that much, if we have leptogenesis from oscillations, then of course it looks different. So here, there we go. I mean, what I have here usually that I have, much smaller. I mean, here I have small couplings, but I also have small masses.
Mm-hmm. Yeah, right. Yeah.
And here, of course, the masses of the right-handed neutrinos are much smaller. They can have an effect. So, but I think here again, the couplings are maybe tiny. But I think I have to admit, I'm not aware of, on top of my head, of a literature that exactly describes here the direct connection of the CP violation in these scenarios with respect to collider searches. Of course, what people do is to look into right-handed neutrino searches. I mean, this is for sure, there's a lot of literature, but I guess that usually, it's suppressed by the small couplings or by the heavy masses.
Mm-hmm. Okay, thank you very much.
You're welcome.
I don't see any other hand raised. If not, I have a question myself concerning the first part of your talk. You said that, okay, we need a strong first order phase transition in order to avoid the washout. But also we need a source of CP violation in order to have the right number of baryon asymmetry. Do you know if in literature there are schemes, framework in which you can obtain both can realize the mechanism? Because I have in mind, I studied it in the context of composite models, composite Higgs models. You can do it, but it's a sort of, I mean, you need the specific representation of fermions and things like that. So I'm curious if there are some other frameworks in which you can obtain both these two properties.
So I think here, okay, I would claim, but maybe, yeah, I have the feeling that currently there is not the one where one can basically do both, in the sense, okay, no, this sounds maybe too strong, what I didn't want to say. What I wanted to say is that, for example, with the MSSM, of course, everybody was thinking, okay, this is maybe it where we can get everything, right? I mean, we would have still, okay, constraints from the EDMs, but it was somehow from all sides somehow motivated. But I have the feeling right now it's less focused on one or the other model. Of course, there are people, and this is what I would like to refer to those papers, but again, this is not a complete list, it's just examples. So I don't claim here that it's all what is there, of course not. But here, for example, here in this paper, really people try to have both. So they took their 2Higgs doublet model, they added, I mean, what people did already with the extra topio-Kaba coupling, and here they really try to confront the EDMs, the Higgs physics, and also the first order phase transition together. However, if I remember correctly, they do it, but I don't remember that they really calculated the baryon asymmetry precisely in the end. Then you see here, then, yeah, it's the BLSSM. So then people try to adjust the MSSM because we know this is a possibility. And then also to have other singlets or whatever to add new particles.
Okay.
Yeah, so I would say that, I mean, I'm not aware of now the famous model as with the MSSM, but it's still, I think it works in different models, but I think one also has to be fair that it's not easy with the current constraints on the one hand from the Higgs physics and the EDMs.
Yes, it's exactly my feeling. Okay, so I think we can thank Julia again.